In this video, we are exploring function transformations. We'll start with these two functions as our base functions. We're going to relate all the transformations we look at these two functions. So let's take a look at what their graphs look like. Here's the function f of x equals x squared. So we see this parabola with the vertex right at the origin, and this squared relationship between x and y coordinates. So when x is 1, y equals 1 squared. When x equals 2, y equals 2 squared, which is 4. And we can definitely think of the y coordinate as the value of the function. The x coordinate represents what is our input value, and then our y coordinate would be, well, what is the actual value of that function when we put 4 in place of x? In this case, we should get a point all the way up at 16. And 2, 4, and 3, it's above this page, but the coordinate 3, 9 will be on this graph. When x is 3, the value of the function is 9, and the value of the function is the y coordinate of the graph. Here's our other function. It's the reciprocal function, f of x equals 1 over x. So we see some ordered pairs like 1, 1, and then because 1 is the reciprocal of itself, but how about 2 and 1/2, 3 and 1/3, 4 and 1/4, 5 and 1/5, and so on. And in between 0 and 1, these x values, remember how reciprocals work. So if x equals 1/2, the reciprocal of 1/2 would be 2. At x equals 1/3, we have a point up at 3. When x is 1/4, we're up at 4. And we see a vertical asymptote. We don't actually have points when x equals 0, because we know that that would make this expression undefined. So there are no points of the graph when x equals 0. We have the graph getting very, very close to the x-axis, but not actually crossing the x-axis. So these are our two base functions. Let's first get into the x squared function. We're going to make a table of ordered pairs that we can look at as we do the transformations. We'll choose for x values just integers between -2 and +2. And we know that the function value can be found by one at a time. We take this x value and put it in place of the x in this function here. So -2 squared would be +4, and then our other points at +1, 0, and again positives because this exponent 2 is forcing every result to be a positive number. So every value of this function is positive. We can anticipate what the graph would look like. Since we know that every function value is positive, we know this graph must be completely above the x-axis. If it's below the x-axis, that means it's a negative function value. So already we can see that this should be a graph entirely above the x-axis. And one idea that we're incorporating all along the video is strengthening how we see the relationship between the ordered pairs and the graph. So that's why I'm talking to you this way. So again, back to our graph, and we see all of those ordered pairs, 0, 0. When x is 1, y was 1, and when x was -1, y was still 1, and so on, 2, 4 to -4. Now let's explore our first function transformation. We're simply going to take this f of x equals x squared and multiply a number to this function. So we still have the x squared part, but now after we square the value of x, we would then multiply it by 2. So a table of ordered pairs, we can think just substitute the x value in place of this x. Order of operations says we have to do the exponent first, and then from the result we multiply by 2. So we get these function values, and we can see the multiply by 2 going on, that there's a factor of 2 comparing our original function x squared to this one, which has the times 2 in front of it. So we can clearly see the effect of that. Now, what will this do to our graph of x squared? Since each y value is now twice as much as what it used to be, we're stretching this graph up vertically. Now, the point 0, 0 is still there because points on the axis are tied there when we're thinking about what happens when we multiply. It definitely does stretch out points, but we don't pull off of the x-axis. We don't pick this graph up and move it. We just think about each point being now twice as large as what it used to be. So the point 2, 4 is now up here at 2, 8. The purple is our transformed graph where we're multiplying by 2. So to take a graph and multiply it by 2, it makes each function value be twice as big as what it was before. So the graph is really being stretched upward twice as long as what it was. Let's try to see the same effect with the reciprocal function. Here are our ordered pairs when x is negative 2. In place of this x, we have 1 over negative 2, basically negative 1/2. Or I could just think reciprocal. Maybe that's a little bit quicker. Negative 1 is still negative 1. Our 2 becomes 1/2. There's that graph, the reciprocal graph, just showing it to you over and over again. We'd like to have a good visual concept of what these graphs look like, really memorized. So it's a good idea to have a good mental picture of some of these base graphs like x cubed and the reciprocal graph, and maybe a couple others, x to the third, absolute value, and so on. So what happens when we multiply this function by 2? 1 over x times 2 becomes 2 over x. Our table of ordered pair solutions, negative 2 in place of x. So it's really no longer a reciprocal function, but I can see 2 over negative 2 equals negative 1. If we have 2 over negative 1, that equals negative 2. X still cannot equal 0, so that's undefined. If x equals 1, now our function value is equal to 2, and the last point here. So we can still see our function values have all been doubled. Multiplying our expression of the function by 2 means that all of these y coordinates are doubled. And when it comes to the graph, it means that everything is twice as long as what it was before. The point at 1, 1 has been stretched up to 1, 2. Our point at 2, 1/2 has been doubled, stretched up to 1. So every point is twice as high as it had been before. We're thinking of this as stretching the graph up and down, stretching it away from this x-axis. So the point at negative 2, negative 1/2 has been doubled to negative 1. Every y coordinate doubled because we did it times 2. To show you a couple of quick examples, what if we said let's do it times 3? Here's 3 over x, and we can see we've been stretched even further vertically. Now you may see some other kind of stretches going on, but I do want to emphasize the algebra is describing the change as a vertical stretch, each point being shifted by some factor. This time it's 3 times as large as it was initially, stretching each of these points vertically. And in the next video, we'll talk about why some of the stretches look like maybe it could be one kind of stretch or a different kind of stretch, that they maybe look like they're doing the same thing. We'll definitely cover that soon. And one more here is 5 over x. So the point at 1, 1 has now been stretched all the way up to 1, 5. The point at 1/2 is now times 5, 2.5, and so on. And the same here, stretched downward when the function values were already negative, they got stretched even further negative. So stretching away from the x-axis. Let's look at a couple of quick other examples for the x squared function. There's 2 times x squared, 3 times x squared, so we're stretching this function at every point 3 times as large as what it was originally. 1, 1 is now 1, 3, and 2, 4 has now become 2, 12, stretched up off the page. So we can summarize what we've seen here by saying that if we multiply the function by a constant, multiply by 2 or 3 or 4 or any number, we know that it's doing some sort of vertical stretching. We'll represent this by saying a as some number being multiplied to the function. Now it doesn't look exactly the same as what we had here, but remember we're saying our function equals x squared, so doing 2 times x squared is saying we are doubling this function. We're taking this and multiplying by a 2 out front or some other number. So this is how we're representing the act of multiplying a number to the function. And the result is that it's going to stretch this graph out vertically. Now, so far we've only looked at numbers that are greater than 1, thinking about the function values being larger and stretched up and down, stretched away from the x-axis. But what about if we multiply by some kind of fraction? So let's look at multiplying by 1/2. In our table of ordered pair solutions, now each function value is 1/2 of what it was originally. 4 cut in half down to 2, 1 cut in half down to 1/2. If we look at the graph, thinking of each of these points now being half the size of what it just was, it is compressing this graph. It is squeezing it closer to the x-axis. Each point has been decreased by a factor of 1/2. What we multiply to the function is changing its vertical coordinate, its y coordinate, the value of the function, all one and the same thing. So if we multiply by 1/2, we are saying cut everything in half, cut it down, compress it to half its size. And if we multiply by 3, we're saying every vertical coordinate should be 3 times as large, and the result is stretching this graph vertically, away from the x-axis. If we look at the reciprocal function, multiplying by 1/2. Now I definitely would want to simplify this, but I'm keeping it written this way so we could think of this explicitly as multiplying by 1/2. We can see it clearly. Our table of ordered pairs, it's doing what we would expect. Each function value is now half of what it was initially with this reciprocal function. -1 cut in half to -1/2. Undefined, still the same. Everything else here cut in half. Do we see this vertical compress, that we're being squeezed closer to the x-axis? The point that used to be at 1/2 2 has been cut in half down to 1. The point at 1/2 has been cut down to 1/4. Every point now half what it used to be, so we're being compressed toward the x-axis. The points here that were negative have become less negative. They're also being squeezed toward the x-axis. So we can call this a vertical compress when we're multiplying by a fraction, some number that is in between 0 and 1. And it really fits in with what we saw when we're dealing with numbers that are greater than 1. You multiply anything by a number greater than 1, it grows. And if you multiply anything by a number that is between 0 and 1, it decreases in size. So the same exact thing is happening to our graph. There's one last part to consider. What if we multiply by a negative number? For this example, let's just look at the result of making the value of the function negative. So all of our original function results are now opposite of what they used to be. This function that provided all positives, remember, order of operations says do the exponent first, and then the negative really fits in as a multiply step. It's multiplying by -1. So if we plug in -2, -2 squared is +4, but then the negative changes it to -4. So it changes all of these values to negative, except for 0, of course. Here's the base function x squared, and multiplying by a negative is changing all of our function values to negative. So where we used to go up on the y-axis, we're now going down on the y-axis. What we're seeing is a reflection. It's a reflection on the x-axis. You could still think of it as some sort of vertical change. It's helpful to think of multiplying a number to the function as changing it vertically. So multiplying by a negative number is causing it to be reflected vertically. Now, we do say that we're reflecting it on the x-axis, or reflected over the x-axis, because our points are moving over the x-axis, but it's reflected vertically. So let's check it out with the other function. Multiplying by a negative makes this a -1 over x. Our function values have all become opposite. So from this base function 1 over x, where our vertical coordinates were positive, now they're going to be negative. And where they were negative, now they are positive. So we see another reflection. And you may say, well, it looks like it could be reflected on the y-axis also. And again, that's something that we'll show in the next video. For now, think of making the function negative as reflecting it on the x-axis. What was up is now down, what was down is now up, so reflecting it on the x-axis. So if we were saying that a was a number like -2, we would incorporate, first of all, that it's still stretching our points by a factor of 2. Every vertical coordinate is now twice the size of what it used to be, but also, since it's a -2, we have to reflect that graph. So you could say technically we should have absolute value of a is greater than 1 and absolute value of a is between 0 and 1. But think of this as when a is positive, and that if a becomes negative, you must also incorporate that this graph is being reflected. If we're multiplying by a -1/3, it's still being squeezed to 1/3 of its size, closer to the x-axis, but then it will also be reflected on that x-axis. So that sums up our first function transformation when we multiply the function by a constant.